Yeah, thank you very much for the invitation to talk about SNEWS. So kind of building a little bit off of Barry's topic, which is also great because he did all the background. So thank you. Right. Just I guess I don't know, just to add a couple little things to that, just here and there. Just if you well, I guess not too many people here actually remember maybe 7, 8, but of course, yeah. But of course, the story, the story that you hear is, here you have your nice field of stars, get a bunch of neutrinos. 3 hours later, you see light. Of course, and then 15 years later, that's actually 15, 20, anyway. Decent time later, you see that kind of a picture. Of course, this is not exactly how it happened in real time. It's actually that which was observed first, and it's only and then people looked later on in the neutrino data and found, oh yeah, actually there are some neutrinos here. And part of that, of course, is from the fact, well, we'll get it. I mean, well, actually, Barry already talked a little bit about the timing. Here's an updated, I think the slightly more updated sort of supernova rate estimate. So some people say, when they sort of go through all the historical records, maybe the rate is 1.6 plus or minus 0.5 per century. Yeah, just same point. Galactic core collapse supernovas are extremely rare, also extremely rich in physics. And I just like that picture because it's just mind blowing to me anyway, that Andromeda is actually that big in the sky. But that's because I tend to be underground rather than looking at the sky. Right. So there was the point about the timing. Yeah. So this is sort of kind of like the neutrino light curve for different neutrino flavors. Also plotted, and then the horizontal axis is log of the time, which is why 0 doesn't exist here. So with the core collapse supernova, you would see, of course, this massive, you have this massive luminosity, neutrino luminosity. You also have significant gravitational wave luminosity, though the waveforms are a bit less certain there. The neutrino predictions are a bit, at least certain, many of the general characteristics of the neutrino luminosity are actually pretty well established, or at least people feel that they kind of understand this. And then, of course, yeah, the optical component comes down here, possibly several hours later, possibly, as noted, much quicker. So yeah, it is the race against time. Neutrinos are the starting gun. Race takes, I'm slightly more optimistic. I say once in a career, okay? So, people who are starting off, you may actually see it in your career. Of course, those of us who've been waiting since 1987. So yeah, you don't know when, you don't know how long it's going to last. So you want, and you want all hands on deck, every possible radiation, every possible. So as a result, there was SNEWS. Actually, SNEWS as a network of neutrino detectors goes back even into the last century. But it's had automated operations since 2005. And the way that has worked is that there's been a 10-second coincidence window of whatever detectors were actually involved at the time, generally about half a dozen detectors. That does actually include Super-Kamiokande still as a component to that. So I think one of the first notices, as Barry pointed out, does actually go to the original incarnation of SNEWS. Now, given that this is actually automated operation since 2005, the environment in which it worked, or in which this was designed, reflects that time. So you get to expect, it's designed with a fake rate of about once per century. Okay. This is apparently because the astrophysicists said to the particle physicists, if you ever give us a false alarm, we'll never believe you again.
They've all retired now, it's all right, we're more generous.
Yeah, so it's, things have changed, but at the time, and the way that the system is still working right now, there's a high burden on experiments for high quality input alarms, and the coincidence can actually be delayed quite a bit as a result. Okay, so this is actually still in operation. And of course also has some other side effects. You know, if you have a fake rate of only that amount and no galactic supernova since 2005, the people who organize this occasionally get calls of this sort. So yeah, so we're looking at the next step, and you know, things have changed quite a bit. Now we can actually talk about some more, you know, kind of like things like with fake rate and so forth. I mean, a non-zero fake rate. But then when thinking about how to upgrade SNEWS, also there are other questions that come up because, you know, obviously questions like, you know, where is it? Where is it coming from? You know, what is it? When? How? Et cetera, et cetera. You might say back in 2005, it was quite unfeasible to answer such questions. Nowadays, since we have more sensitive neutrino detectors, dark matter detectors, we have more different techniques. We can actually start approaching these things. So the SNEWS 2 goals, you know, several of them reduce the threshold for generating the alerts. We're actually kind of aiming for a false alarm rate of about once per month. And this will serve the purpose of fire drills, sort of proof of life, also backgrounds. Though actually, this did make me wonder a little bit about how that would interact with products like Astro-COLIBRI, where a lot of times things are actually signaled that might be interesting. So I'm not entirely sure how that works. That would be an interesting discussion to have. Also, yeah, so going on with SNEWS 2, reduce alert latency, provide pointing information and other real-time calculations. Of course, you know, we also heard from Super Kamiokande, I mean, from Barry's talk that, you know, they already have excellent pointing in at least in a number of domains. Also, yeah, we had the goal of implementing a pre-supernova alert, and then develop follow-up strategies, prepare the astronomy, you know, help prepare the astronomy community. And part of this project, this is an NSF-funded project, or largely NSF-funded, engage with amateur astronomers and citizen science communities. So there's a white paper on this. There's a more recent paper on the alert system that just came out. There's also a web page which also can sign up for things and so forth and so on. Okay, so SNEWS 2 will is actually already starting to encompass a number of these other experiments. So quite a wider variety of neutrino as well as dark matter experiments. And also it's good to know, you know, the SNEWS activities, they're actually pretty open, they're also pretty informal. So there are actually quite a few opportunities for just sort of connections and research collaborations. So I'm actually, you know, as you see, there will be a bunch of papers that have been coming out, which result from this nice open collaboration. Now, what I'm going to concentrate on a little bit is this are some of these real-time calculations, which include pointing. So now, of course, at the time when we started this, the Super Kamiokande latency was more like the several hours, I think. Okay, so I think the fact that they have gotten a lot faster is fantastic. Of course, you know, so in certain circumstances, this is just going to be redundant and less precise, possibly quicker still. But you know, in some sense, we do need all these complementary capabilities, such as, you know, if it is more distant, or like, in fact, I think Super Kamiokande is off right now.
It can be off now and again, so
yeah,
coverage is, you know.
Yeah, so you know, you do want to sort of, you know, you want to make sure that you're up all the time if at all possible. And then you have the other possibilities for calculations, such as, you know, making an estimate of the distance, as well as sort of supernova features. Oh yeah, I should emphasize, when we're talking about these real-time calculations, we're not talking about doing a full astrophysical analysis of anything. We're actually just trying to get the rapid calculation of observationally relevant quantities that can be useful to the observer community afterwards. Okay, so on pointing, so, you know, obviously, you know, if you have enough electron elastic scatters, that's going to dominate the pointing in the end. Okay. But to make, you know, to have something very fast, something very robust, also with, you know, sort of increased lifetime, though less precise. You can also use just, triangulation. This is a pretty, or multilateration. Yeah, so we actually have a number of, well, actually this paper should be coming out very soon based upon the first event times. And actually what we need to get here as well, and what we've actually put a lot of work on, is how do we actually calculate the confidence intervals in a good rational way. And we can actually show that these are in fact just about the right ones. Yeah, and you can get, let's see, so yeah, this slide actually sort of, it kind of shows two things, or I might say it's doing two of those things at once. One is that actually, it's pretty well, or it was pretty well established that if your neutrino light curve has some very nice sharp features, such as you would expect from a black hole forming, you can actually get even better pointing. So this was actually an illustration of how that pointing improves. Yeah, then as for the more observationally or potentially observationally relevant features, there's the realization, of course, that not all supernovae are alike. You have all sorts of things like, well, you could have a long accretion, you could have, well, again, these abrupt cutoffs. Another one is sort of having secondary bursts. So obviously, if like a black hole forms, that's quite observationally relevant, since you may not get the optical component at all. Okay, and there is that question as to how long you want to be staring. After you've done your nice tiling and everything like that, how long do you actually want telescopes to be staring at particular patches of space? Also, it's just, there are other potential things that you could be anticipating here, which could be observed. It would be good to have some sense of this before it actually happens. Right. Okay. Well, yeah. Just something going back on direction. Let's see. Distance estimate. Sorry about that. Yeah, I'll go nearly done. Right. Yeah, we do have a distance estimate based upon different aspects of the neutrino light curve. Obviously not very precise, but still potentially important because, again, where the supernova actually happens could change the optimal observational strategy, especially if you get a lot of dust cloud extinction. And yeah, I should point out that there are a couple other things that have been going on in SNEWS. SNOOPY is actually something which, we've collected a lot of the supernova models together so that you have kind of a nice unified interface of them. I mean, so that you can actually use hundreds of them as opposed to learning for every single one of them. Various event generators. We have regular seminars. One of our colleagues, Marta Colimer, who I think was from around here, is organizing that. Also, we have a catalog of, we might say, likely candidates. So we can concentrate on those as well. And yeah, working with follow-up communities. I'm feeling I just spent way too much time in the introduction. So anyway, all these kinds of things are potentially interesting and can be, should be discussed. Right, so just yeah, the neutrinos start this race for the galactic core collapse supernova. We want to get the most bang out of it, well, literally. And yeah, we're getting set, you might say. It should be sort of or we're trying to get full operation of this by the end of the year, and then actually have that transition from the old SNEWS to the new SNEWS. Basically at the end of this year.